Back to the IPv4 header here, the next field I want to talk about is the checksum field, and it can be found at the 10th byte offset from 0 and is a 2-byte field. So you see it there on the right in the third column just before the source IP address. Now, the goal with the checksum is to provide a way for systems to validate the integrity of the IP header. Not as much of a problem with modern networks that are fast and timely, but especially back when IP was created, and that was quite some time ago, you really had to be concerned about data corruption on really high latency links. And the last thing you want is a corrupted IPv4 header, because it means data is going to be probably not sent to where it needs to be, or some other type of weird issue is going to occur that's going to be really hard to troubleshoot. So the idea here is you really have an interplay between the host that creates the IPv4 packet and every host that receives it. So that includes both intermediary routers and a destination, a terminal host. So at the point the IPv4 packet is constructed, you have all the IPv4 header fields figured out. Those are all ready to go. The system takes those fields and does a simple calculation on them to determine a checksum value. Now, we're not going to get too much into what that calculation is. It's pretty straightforward, a little beyond our scope, but it involves grouping things into groups of 16 bits and inverting the bits there and then adding those up, and that's what gets you your checksum value. Now, so it's a very simple calculation. There's a good reason for that, which I'll talk about in a minute. But the idea is you perform that calculation based upon all the values of the things in the IPv4 header. Every intermediate or destination host for that packet, when it receives the packet, does the same calculation on all those fields and compares it to the checksum value that was put in by the transmitting host. If those checksums are the same, good. That means everything's good to go. We're all great there. If they're different, that means something in the IPv4 protocol header has changed in transit. Now, that could be due to some type of signal degradation, something physical layer related, or it could be through some type of malicious means. Someone's trying to manipulate traffic, something of that nature. So in the case that the checksums do not match, generally the recipient will discard the packets. And I say generally because there are some edge cases, but for the most part, the recipient or intermediate host will discard the packet and drop it. The idea and the hope there is that the IP packet is paired with a reliable transport protocol like TCP that will retransmit the packet. Hopefully it makes it intact this time, or paired with some type of application layer 7 protocol that's going to have some mechanism built in to compensate for this and resend packets as needed, so no data is lost. So that's what we're talking about. We're talking about checksums. Now, one more thing worth mentioning here is that with checksums, think about it this way. One of the things we talked about a minute ago was, I'm taking an IP packet. If I send it out to the internet, one thing that has to happen as part of network address translation is a router has to rewrite the destination IP address, or the source IP address, to match its own IP address, right? Because the IP address of the transmitting host is not routable on the network. So no matter what we're writing, in this case we're writing IP addresses, if we're rewriting contents of that packet, what's that going to do to the checksum? Well, that's exactly the type of thing the checksum was meant to prevent from happening, was changing the value of an IPv4 header in transit. So one of the things routers do when they rewrite those addresses, those source or destination IP addresses, is they actually have to recalculate the checksum. So as a result, the calculation for checksums needed to be very, very simple, which is why it is very simple, and why it's maybe even a little bit fallible. I won't get into the details of that, but if you take two 16-bit groupings of data from an IPv4 header and invert both of them, then the checksum will still be the same because those numbers will still add up to the same value. You can look at checksum collisions and look up some resources on that. But all that to say, it's a very simple, it's a very fallible algorithm, but it's made simple because every router is having to do it on every single packet that it routes and rewrites the source or destination IP address for. So keep that in mind. This is happening with every single router that a packet traverses along its path to its destination and along its return trip as well. So checksums are important in order to make sure we have and maintain integrity of the IPv4 header. Worth noting, this is just the IPv4 header. It's not the entire packet, just this header. There are other checksums that are involved with the data of a packet and other reliability functions that we'll talk about, but this checksum is just the IPv4 header, and it's found at the 10th byte offset from 0. Pivoted back over here to a instance of Wireshark because I want to show you what it looks like when a checksum doesn't look correct within the application. So I'm going to show that to you here. And what I've done is just opened up the same file we've been looking at, http:/google.pcapng. In this case, I've gone ahead and renamed it to IP_checksum.pcapng because I'm going to be making a couple changes to it, and I want to preserve the integrity of the original file. Now, in this case, I've highlighted the first packet here. I'm going to expand the IP header, and you see this looks pretty straightforward. We have a source and destination IP address. We're talking to Google here, and in this case, we have a header checksum value of 535C. Now, something of interest on my configuration right now is that validation is disabled. So you see below it, header checksum status unverified. So there's actually a configuration option which you have to turn on in order to be able to validate checksums properly. I've actually disabled it here because of some of the captures I've generated had intentionally bad checksums, and it was colluding the analysis process a little bit, so I've disabled that. I do want to show you where that configuration option is, though. To get there, you go to Edit and then Preferences. We go to our protocol specific settings here. I'm just going to type IP in, scroll down to IPv4, and we have an option here to validate the IPv4 checksum if possible. I'm going to go ahead and check that and hit OK. When I do that, you see we have a change here, and it says our header checksum of 535C is correct, and that our header checksum status is good. So this checksum matches according to the data that exists in the IPv4 protocol, so everything is great. So what I'm going to do next is go ahead and close this out because we're going to make a change. Behind it, you see I have WinHex open. It's always a good day when we get to open a hex editor. In this case, I've highlighted some bytes, AC101080, and this is actually one of the IP addresses in the first packet. So what I'm going to do is make a quick change. I'm just going to change this 8 to a 9. That's a very subtle change, but it's enough of a change that it will force the checksum to be incorrect, and we should see that reflected when we open the packet capture in Wireshark. I'm going to go ahead and do that now, and sure enough, there we see it. The very first packet, the one that's selected now has a black background and a red foreground here. If we go down to the packet details window, we see the IP header is highlighted with a red background and black text. If we expand that, we see that the header checksum is noted as being incorrect. It is now 535C. It tells us, Wireshark does, that this is incorrect, and it should be 534C. So what's happening here is Wireshark is actually doing the header calculation for us, the check calculation, what it is, what it should be, and it's comparing those and telling us that something is wrong here and we have a bad checksum and that something has been corrupted or changed along our path. Now, this is an after the fact issue. We've captured these packets and we've captured the ones with an invalid checksum. Of course, our packet collection tool will capture everything. It's not going to reject things like a router would or a recipient system. If this were a real system that we're receiving or an intermediary recipient of this packet and it saw this incorrect header checksum, it would most likely reject the packet and that data would be dropped, ideally to be resent again by some other application layer process or transport layer protocol running on the source system. But nonetheless, you see this is what you would see if you encountered a bad header checksum. One quick thing to note here before we leave this specific example is you notice here how it says this may be caused by IP checksum offload. Well, it's because of this reason that IP checksum validation is disabled on by default on most Wireshark installations, and that's really due to a feature called offloading, and it really relates to how Wireshark captured packets and features of how packets are processed at the network interface level versus the CPU level. I won't get into too much detail on that here. There is a Wireshark wiki article you can read that discusses capture setup and offloading and why you may see these issues if you do have IP checksum, header checksum validation enabled. So that's something to be concerned about and something you will see if you have that enabled. Anytime you see that, it doesn't always mean that the packet's been tampered with or corrupted, and that's one reason why it's often disabled, and I actually leave it disabled myself. But if you have a reason to use it, you now know how to enable header checksum validation for the IP protocol and exactly how that works and what that looks like.